Hello, my name is Natalia Gervits. I am from Lebedev Institute, Moscow, and I'll tell about magnetic and crystal structure of turbine-doped bismuth ferrite. Multiferroics are the materials which exhibit more than one ferro properties, such as ferromagnetism, ferroelectricity, or ferroelasticity. There is a classification of two types multiferroics. The first type are the multiferroics with those properties of same origin, and the second type of multiferroics are the multiferroics with properties of different origins. Bismuth ferrite is a very prominent multiferroic. It drew attention to itself more than 30 years ago, and since then it's intensively studied. There are several problems which have to be solved for vast application of this multiferroic, bismuth ferrite, in technique, in usual life. The first problem is high leakage current. The second problem is weak magnetic electric coupling. And the third problem is that a magnetic moment of the bismuth ferrite is zero due to the existence of a spatial spin modulated structure. Our study is devoted to suppression or even destruction of this spin modulated structure. The crystal structure of bismuth ferrite, of base compound, is rhombohedral. Usually it's showed as hexagonal. It's more convenient for some studies. When bismuth ferrite is doped with some atom, for example, terbium or strontium or lanthanum, different ones at the A position, when they stand for bismuth, the structure changes to orthorhombic or even cubic. So I forgot about this one. There is two axes. One axis is for polarization vector. It's directed along this axis, or this axis in hexagonal structure. And the other axis perpendicular to this axis is the axis of propagation of spins, spatial spin modulated structure. I'll tell about it in the second slide. It's propagating along this axis, along this direction, or this direction. A spatial spin modulated structure is cycloid with period of 62 plus minus 2 nanometers depending on temperature. This cycloid is located in the plane which is constructed on two vectors, on the vector of polarization and on the vector of propagation of this cycloid. This cycloid leads to locking of the magnetic moment and zeroing it, in spite of the fact that it can be very, very huge in this bismuth ferrite and derived from its compounds with doping. To destruct or suppress this spatial spin modulated structure, usually I used several methods. The first method we are using it here is doping. Doping of A sites, usually A site with different atoms. The second one is applying external magnetic field, and it can be applied at different stages. For example, it can be applied at the stage of synthesis, and it can be applied to the already synthesized sample. And nanoscaling. When you go to nanoscaling, you have some specific magnetic effects which can solve the problem with the locked magnetic moment. The zero field NMR spectrum has a characteristic form for cycloid spin modulated structure. If the spin modulated structure is isotropic, you have only one line. Here's the enveloped antiferromagnetic vectors of the spin-modulated structure. If you have an anisotropy of the spin of the vectors of spin-modulated structure, you have this specific two horns line. This line with two peaks represents the antiferromagnetic vectors standing for the vectors that are directed along the propagation vector, and for the vectors that are directed along the polarization vector perpendicularly. And this is the vectors which are in the middle stage. And if the vectors are, for example, look like this, you have this type of spectrum, and this is called easy axis anisotropy. You see, this is the easy axis, and the vectors are directed along it. And if you have the collinear structure, for example, this type of collinear structure, when all the vectors are directed along the axis, along the propagation vector, you have only one line. But if you look at this line and this line, you see that this line is in the center. It can be centered at some frequency, and this line is shifted to the right, and it is shifted to the right to the easy axis type of anisotropy. But there are two types of anisotropy which can be realized in this structure. This is easy axis anisotropy with the highest frequencies dominating, higher frequencies dominating, and the easy plane anisotropy when the lower frequency atoms vectors are dominating. And this type of anisotropy stands for the spatial spin modulated structure with vectors, with most of the vectors directed along the polarization axis, polarization vector. So when we see this type of spectrum and with different intensity of the peaks, we can say that it's some type of anisotropy, and it's anharmonic. Anharmonicity parameter is a parameter that comes from the fitting of this spectrum by complete elliptic Jacobi integral, and this parameter comes direct from this integral, and it tells us about the non-symmetricity of this spectrum. For example, when you have anharmonicity parameter equal to 1, almost 1, you have only one line shifted to the right for this type of easy axis type of anisotropy. And when anharmonicity parameter is 0, you see the symmetrical type of spectrum. Now to the samples. The samples we synthesized in MIRA by Pokatilov's group are 10% iron isotope enriched. They are bismuth ferrites with terbium doping of this content 1.5, 3, 5, 8.5, and 16%. We performed X-ray analysis of these samples, and we found out that all the samples from the series are still in rhombohedric state. In spite of some literature that's sometimes in literature it's said that somewhere around 15% doping, it's already orthorhombic. And we found out that the rhombohedric angle is growing since the terbium content is increasing, and it has a tendency to become 19 degrees as it was expected. Anharmonicity parameter for some of the samples for 1.5, 3, and 5% doping samples, we didn't manage to determine for the present moment, because there's some strange situation. We have different dependence of intensity on pulse amplitude and on different spin-spin relaxation for the spectrum, for different points of the spectrum, for left and for the right peaks, and we still do not know how to measure it right. But what can we say from these three samples? We can say that they are there is a spatial spin modulated structure. We can say that signal is very, very intense. Signal on iron is very, very intensive, and that the frequencies of the peaks are stable. So the anisotropy of the spatial spin modulated structure doesn't change. Then we can see all the spectra in one. And what can we see here? This left wall, maybe it's speculation, but I see it's this way. This left wall is the same for all the spectrum. For example, if we expect the destruction of spatial spin modulated structure, we would have seen the symmetrical destruction. So we would have seen some symmetrical line. It would be broadened there and there. And when we see even the red spectrum, the 16% spectrum, we see that the left burden of this spectrum is in coincidence with the smaller doping, with the less doping, and it's broadened to the right, which tells us that the spatial spin modulated structures presents even here at 16% doping. And moreover, we found out that there is a high field additional line. And this additional line is located here on 75.85 megahertz. And we have found the same lines in other series of samples. I'll tell about it a bit later. And there are the most interesting samples. The samples 8.5 terbium doping and 16 terbium doping. Here we can see that this one is totally anisotropic, and that the anharmonicity parameter is maximum. It's almost 1. When it is 1, it can be described, the magnetic structure can be described as totally collinear. So these, and this is the easy plane anisotropy type. So we can say that at 8.5% terbium doping, our magnetic structure becomes collinear and easy plane anisotropy. But when we make the doping of terbium, when we add some terbium to this sample, and we see the 16% doping terbium, we again see the remnants of this two-peak structure, and we still see this two-peak structure, which says us that the spatial spin modulated structure still is preserved, and the M anharmonicity parameter is a little bit smaller. So maybe we were so lucky to found out to synthesize this sample with collinear structure and found out that there is one with collinear structure. Now about high frequency line. We have observed this high frequency line in other bismuth ferrite based doped samples, in samples with lanthanum doped samples and in strontium doped samples. In lanthanum doped samples, we found out that the intensity of this line is growing along with upon lanthanum doping, almost linearly. So we think that this line is connected with presence of dopant atoms in the immediate vicinity of the iron atoms. But For strontium, the signal was not good enough to tell anything about the intensity, and for terbium, we do not see such law of intensity growth. So maybe it tells us that the terbium is not just scattered in the sample, maybe it's clusterized, but it's very, very arguable. And we see this high frequency line in different series at different frequencies. For lanthanum, it's 76.15. For strontium, it's 76.35. And for terbium, it's the smallest high frequency line, 75.85. These are the conclusions we've made during our work. It's not finished. We have a lot more to investigate. And the main conclusions are the synthesization of the series, rhomboedic structure, presence of the spatial spin modulated structure in all the series, and anharmonicity parameter of the cycloids at 8.5 terbium doping is maximum, while at the further terbium doping, it tends to be a little smaller. That's all. Thank you for your attention.
Thank you very much. Maybe somebody has some questions. Please.
May I ask?
Of course, yeah.
Thank you for your presentation. And there is so-called factor of amplification in magnetically ordered substances. This factor can be dependent on the microstructure. Have you taken it into interpretation?
No, we haven't. We're thinking about it, but no, at the present time, not.
Yes. What is the order of the factor of amplification?
Excuse me,
100, 1000, or maybe.
I'm not sure. I don't want to just.
You are not interested in this. Thank you.
I am interested, but I'm just trying to understand it.
And I have also one short question. Since generally some rhombohedric angle changes, we may expect that temperature phase transitions also shift from the temperatures in undoped sample. Do you know something, if it is known about changes of phase transition temperatures in terbium doped samples?
I don't know it. Maybe it's measured somewhere, but we work with liquid helium temperature, so
no, you
didn't come up.
You cannot see these results, but maybe in literature there is some information about changes in phase transition.
I haven't looked it up, but I definitely will look it up. It's very interesting. Thank you.
Thank you very much.